All right. Welcome, everyone. My name is Casey Wang, and I am a co-PI on the Fabric project. Thank you all for joining us today for the 16th installment in our Stitching Together Innovation with Fabric users. Today, the webinar will be led by Dr. Peipei Zhou. Next slide, please. Before we begin, I'd like to share a few housekeeping items. The webinar will include a live question and answer session following the presentation. Please note that the Zoom chat feature has been disabled, so if you have any question, please type it into the Q&A box at the bottom of your Zoom screen, and we will be answering them during the Q&A session. And last, this webinar is being recorded, and we will be sharing that with all the registrants. Next slide, please. Today, we are joined by our presenter, Dr. Peipei Zhou. Peipei Zhou is an assistant professor of engineering, and she is currently leading the Customized Computer Architecture Research Lab at Brown University. She received her BS in Electrical and Computer Engineering from Southeast University in 2012, and her master's in Electrical Computer Engineering and PhD in Computer Science from the University of California, Los Angeles. Her research focuses on customized computer architectures and programming abstractions for applications including healthcare and artificial intelligence. She is the recipient of the 2026 NSF Career Award, and she was selected to participate in the 2026 National Academy of Engineering Granger Foundation Frontiers of Engineering Symposium. Her research has received the 2025 IEEE ACM ICCAT 10-year retrospective Most Influential Paper Award, and the 2026 ACM IGSC Best Paper Award, and finally, the 2019 IEEE TCAT Donald O. Patterson Best Paper Award. Next slide, please. I will now pass on to Dr. Peipei Zhou to begin the presentation.
Thanks, Dr. Wang, for the introduction, and thank you, Chelsea and Dr. Wang, for moderating this session today. Chelsea, do you think I can turn on my camera? 1 second. Okay, start my video. Cool. Great, everyone can see me, right? Okay, cool. I can see my face now. Thanks, everyone. I'm very happy to join Fabric seminar, and I'm very excited to introduce our latest research infrastructure called MRI project, the Spectrum Testbed, which will be connected to NSF Fabric Testbed in this fall semester, and providing this shared computing infrastructure for next generation computer system research. Before I dive into all those details, I also want to highlight a little bit of my research and also teaching. I focus on 3A keywords spanning from those architecture, including FPGA, AI ASIC, GPU, chiplet, to the abstraction, like how we design the compiler and also support these all those applications, including AI and also medical application domain. And I also teach at Brown, and these are the courses I have been offering, including reconfigurable computing, graduate level course, and also undergraduate course, including embedded system design, computer organization or architecture, and also VLSI design. So this one slide, I really like it because it actually brings up a very interesting topic about computing everything and everywhere. So everyone probably noticed that this news announcement between OpenAI and NVIDIA last September, saying that they will do this strategic partnership to deploy 10 gigawatts of a NVIDIA system. And also about 2 weeks later, AMD and OpenAI make another announcement about 6 gigawatts of AMD GPUs, right? And then one question probably popping up is how big is gigawatts? What's the scale? It turns out in this movie Back to Future, this is the movie 40 years ago. They said jumping back and forth in time domain, traveling back to past, it's about 1 gigawatt. So this is the number in the science fiction stories now become the reality. And honestly speaking, I did a little bit of homework and then find out that this 1 gigawatts is about the scale of San Francisco, like a major US city, like power. So that gives you a sense about how big this power it is for the next generation AI system or the data center. And also, this huge computing is driven by those applications. So AI is the driving force behind this. And this is a very beautiful picture that I got from Apple AI, and they show the trend about those AI model size in terms of those log scale. So this y-axis is a log scale about all those AI models, and the x-axis is a publication date. So we certainly see the trend is like from 1955 to 2010, or well, we see this like 1.4x every year in terms of the model size. However, we see those 4x per year after 2010. And AlexNet, which is one of the earliest and also most used deep learning models in 2012, which also is the starting of the deep learning area of all those AI models, only contains about 60 million. And the model size is about like 240 megabytes. And nowadays, like GPT 4.5, 2025, this is a commercial models. And today is like a Kimi K3. This is the largest open weight model up to now. It's about like a trillion size, right? So we certainly see this 100,000x increase from 2012 to 2025, with all those like increasing in the model size. However, another like if we see those huge like computation need from those AI or deep learning applications, so what about this computing system? Can we keep up with those computing systems? Well, Jensen said, of course, we need to build bigger chips. And this is one picture that's from CES 2025 about the GPU chip. By the way, this is not the actual GPU system, but I'll give you a sense about the big scale of this computing system we need. And the right side is a picture showing Cerebrus wafer scale engine. This is like the real silicon. Like it's like a wafer, and they integrated about 4 trillion transistors within one single system. And that's the computing system nowadays we're building more and more, and also to keep up with this application need from the AI models. And this one, which is from this, clearly shows up this semiconductor trend. And with those 2020, this is like 4 nanometer technology all the way to 2030, like with the projection, those advance in those semiconductor technology and also EDA community and also these fabrication community all together pushing scaling up of all those computing systems. So we do see this scaling up means that we can pack more transistor within certain unit area. And also we are scaling out the system, which means that we can now build those chiplet systems in one single package. And with this, we can probably see like 1000x more transistor in a single computing system. However, this 1000x over the over the past decade, it still cannot keep up with this 100,000x increase in the model size, right? How we can mitigate this 100x actual gap? So keep scaling this semiconductor does not help. We need the computing system innovation and also architecture innovation to keep up with this application need. The one answer is parallelization, which means that we can now use one instruction to control multiple data, and that parallelization can help us to reduce the amount of energy in terms of the control, in terms of the communication. And this actually is how the computer system scale in the first place, that we see more and more multi-core CPU and also multi-core GPUs, right? And another is that we need further customization. By the way, this figure is this energy efficiency trend across different generation of semiconductor nodes. So x-axis is the semiconductor node, and the y-axis is energy efficiency, and also in log scale. And this linear scale of the line here actually shows exponential increase of amount of energy that will be used in certain chip area. And if we keep scaling without those parallelization and customization technique, those single chip will burn like as hot as like sun surface. So we certainly cannot keep up with the scaling as like this. So we need parallelization and customization, which can allow us to do more amount of workload without burning all our chips. So customization now is very popular. So GPU is kind of customization. And another example is Google TPU, Tensor Processing Unit, which was first released in 2014. So Google designed their own AI chip, and then deployed that in their data center. So this TPU keeps being updated, and I think from this 2014 to nowadays 2026, TPU already has seen several generations of upgrade. The thing is that those large companies, they can and they have those amount of the time and also the money to do such kind of like large investment for those very specialized chip design. To give you a sense, so if we fabricate certain chips in 12 nanometer, that we need to pay at least $100 million right before we send any of the design. So that's amount of dollar we have to spend as the overhead if we need to do those any kind of like a chip in those advanced technology. So this certainly is it gives a very good like customization if we do those massive production for the chip design. However, this is not good if we only want to deploy certain customized chip for our own like application, or deploy that and then adapt the algorithm in a very agile way and then change the chip architecture according to those new algorithms. If we want to do agile like design like this, we certainly want another type of computing substrate that can allow us to do the customization. So that's exactly why we have been working on using customized computing on field programmable gate array, FPGA, in this place. So ASIC bring us about like a very great energy efficiency when compared to CPU, about like 1000x. And then FPGA give us about like 10x to 100x energy efficiency. So it gives a very good amount of energy efficiency gain compared to general purpose computing. And the beauty part of it is that the field programmable gate array allow us to reconfigure the computing system in terms of the compute part and also interconnect part, so that we can easily adapt this hardware according to the new algorithm. So the left part, I show this overall FPGA architecture. And this way you can see that they have a reconfigurable logic and memory unit so that you can change the functionality within the chip. And then you also have a configurable IO, which allows you to route the data from this source to destination in a way that you want to design. And this adaptability and also flexibility allow us to easily design domain-specific accelerators for various applications. For example, genomics, image and video processing, and the graphic neural processing unit. So right side, I actually show some of those efforts that we have done before using FPGA for customized computing. And the one example is this image and video processing in medical 3D image reconstruction. And by using FPGA at that time, we can get a very good acceleration in terms of the performance and also 10x energy efficiency gain compared to at that time the latest GPU, and also 100x over energy efficiency gain when compared to CPU. And also we have prototyped this genomics acceleration accelerator on FPGA, which shows this that previously if we use CPU for all those genomics application, so this genomics application in this context is called GATK, Genome Analysis Toolkit, which is a software allows these researchers to analyze the human genome and then relates that to certain like diseases. So this whole pipeline in CPU cost about like 48 hours before the acceleration. And after we adapted those algorithms and then deploy that on FPGA, we can finish all those pipeline within 30 minutes. So that is like amount of this acceleration from 48 hours to 30 minutes, about 100x acceleration in terms of the performance. So this gives you some sense of this performance gains from customized computing in either ASIC chip design or FPGA, well as the FPGA has another advantage in providing that we can prototype and easily like change this hardware right on time and right on site. But then you might have a question that at what effort, right? We can. But you explained that to me about the flexibility and also the faster time to silicon instead of waiting 6 months for the ASIC chip to be designed and also to be sent out to the fab and then to wait it among like your device to be in queue, and then this takes like 6 months at least. But in FPGA, you can design that and then deploy that and then download the bitstream and then deploy your application and accelerator right away. That's about like days effort. But the thing is that can every programmer easily design this kind of a domain-specific accelerator by using FPGA or customized computing on FPGA? So the answer is yes and no. The yes is that because we can now create the hardware circuits instead of writing low-level hardware code called RTL or register transfer level code. Now we can write this hardware using C or C++ using high-level synthesis tool. So the high-level synthesis tool is a software that can translate the code you describe in C, C++ to this register transfer level code, which correspond to low-level hardware details. And here is a example about this high-level synthesis code. So the left part, by the way, this is a stencil kernel, which is heavily used in image and video processing pipeline. So it takes about for image processing pipeline, this is a 5-point stencil, which will take the neighboring 4 pixels and the center pixel and then compute the output pixel. And you can certainly see that there are many data reuse patterns and opportunities here. And in high-level synthesis, we can write about less than 10 lines of code here to describe the algorithm. And then you can add a few pragmas to enable this parallel and also pipeline design so that it can increase the amount of this hardware resource you utilize and then reduce the latency to finish this kernel. And that right side is exactly the hardware implementation that you can get after optimizing on this left-hand side code. And I get this hardware and then download the bitstream and then deploy that right away in FPGA. So this with both the hardware flexibility and also the software stack, and then we can deliver customized system design from months now to days and even hours. Because if you write in C or C++, now it can be easy to design and also debug at both ends, which reduce this amount of effort in developing those customized systems. So there are also commercial examples about deploying customized computing on the data center scale using FPGA. Microsoft deployed their AI services and also search services by using FPGA chips. The project is called the Catapult project. And also they have those, at that time, they have deployed this FPGA with customized architecture and also the software running on top of that architecture to more than 5,000 Microsoft data center servers. And the right side, it shows the board they used at the time is Altera board, now acquired by Intel, and now it's Altera again. And this is architecture shows this bumping the wall acceleration. Well, it says that if this data needs to be sent from across different CPU nodes, then FPGA can sit in between and then accelerate a certain part of the application. And then after this, you do not necessarily need to go back and forth to send the data from CPU and FPGA. So that's exactly these motivation and also this background about all those customized computing deployed in this academia and also in the data center, big data center like commercial companies like Microsoft and Google. But in terms of the academia, right, we also want such kind of infrastructure that can allow us to do such kind of a customized computing. And we do have such system now, which is our MRI consortium project. This one, we give a name called Spectrum. And Spectrum test infrastructure is exactly the customized computing system testbed that we would like to allow system researchers and also domain experts to prototype their new customized computing architecture on top of that. And the beautiful part of Spectrum is that we offer different levels of customization and also heterogeneous computing customization in terms of the system, in terms of the chip level, the node level, and also the data center level. And Fabric is the entry point to use Spectrum. We're currently actively working with a Fabric team so that every Fabric users now in the future can have access to Spectrum node if you do another subscription to Spectrum node. And then the Spectrum node entry point will connect you to these nodes, to the Spectrum compute nodes, which will be held in Syracuse University Data Center. So this project PI is Dr. Alex Jones from Syracuse University, and I serve as a co-PI and also system architect at Brown University. So for now, we already have this computer system being shipped to Syracuse University already, and we are in this installation phase and also testing phase now. So we will have a server with 8-way H200 GPU, and also two servers, two 2U servers with H200 PCIe card. So these are in different forms of GPU card. The idea is that if we put those GPU system in this data center node, we want users to either use that as an AI training infrastructure, or they can use them as an AI testing or AI inference infrastructure. And then another beautiful part is that we also have the plan to work with AMD to get those FPGA cards and also this heterogeneous FPGA ACAP architecture. So the name is called ACAP, Adaptive Compute Acceleration Platform, which is a heterogeneous computing system that integrates CPU and AI engine and FPGA programmable logic within one single chip. So with all those three different computing platforms installed in Spectrum node, we first will allow users to either choose GPU for their single chip system deployment, or use the FPGA, or using ACAP architecture for their computing system experiment. And the node level, what does that mean? So node level means that within the same compute node, we do allow we provided this hardware in the first place. That is, we have a 7 to 8 PCIe slot, and then we slide those 4 different GPUs into those 4 different PCIe, and then slide the other 2 FPGA PCIe card in the same node. So that within one node, we do have heterogeneous compute devices as well. So this is another level. Within the single node, you do see different type of computing system integrated in the same server. So this is the architecture overview of about such kind of a system. And we prototype and experiment such kind of computer system to test whether it's working. And this is the phase 0 server that we deployed at my lab here at Brown. So you see, we do have a motherboard, and then we have 7 PCIe slots here. And now we put the GPU in this server. We put a U250 FPGA in the same server. And also we put another smart SSD in the same server as well, which I'll explain a little bit more about that. So in this way, you can see that within the same node, we have a GPU cards, we have FPGA card, we have a smart SSD card, and we do allow users in the future, if you do have another computer system you would like to configure, you can discuss and coordinate with us about the computing hardware substrate you want to have in the future. But this is like the phase 0, and then we are now porting this phase 0 design to phase 1 servers in Syracuse University. And with that saying, this is like exactly this flexible computer architecture that we would like to deploy and also launch in Spectrum node, and ultimately provided that to Fabric users. And another big part of this product is that we need to provide this computing system that is a software layer to allow the users to easily adapt their computer system to map onto those hardware substrate, and then also run their applications, right? So this is the software part. So we provide the hardware part. We also will provide the software part. And in particularly, I would like to highlight a few several projects and also the efforts in enabling this. So I will use one prime demo cases and also user cases, which is Agile project that was published last year in supercomputing to prototype, to test and also experiment this software environment, and also 4 other demo cases, and to discuss about the generality about how you might adopt a Spectrum test infrastructure for your own application. So for the first case study, Spectrum first case study, this one is the agile, lightweight, and efficient asynchronous GPU-SSD integration. So this one is the software that we develop on top of phase 0 test Spectrum node, and discuss about how we can leverage those asynchronous compute I/O between those GPU and SSD to enable large-scale AI applications, so that we can reduce the runtime, increase the efficiency, and also probably can migrate that in the future in the OS level support as well. And this is also a collaboration effort with Syracuse University and the Brown University. So we want to, so in this project, we basically want to leverage GPU system as if like it's not just a compute module, but also this GPU-centric and maybe the accelerator-centric programming model that allow users to easily enable GPU to send and or initiate those IO communication to all those different layers of storage system. For example, when we say storage, we are referring them to including those memory systems in terms of the GPU HBM memory and also CPU memory, and also the storage, including those the hard disk and also solid state disk, and to support all different kinds of applications, including deep learning, all the way to those scientific simulation. So this is a very similar like a trend, particularly on those this AI models versus the GPU memory. But the key idea is that the GPU has certain amount of memory, right? For example, in those Blackwell GPU B200, it only has like 192 gigabytes memory. And if now we want to deploy a AI model, which exceeds more than like a trillion parameter, how we can use one single GPU to enable that? Is that even possible? So the possibility, the answer is yes, it is possible, but with a certain like architecture innovation. So the trillion parameter means that the terabytes of GPU memory needed. But if we only have one GPU devices, that can only give us 192 gigabytes. It's not even efficient to put all those weight in those GPU memory. However, if you leverage the CPU DRAM, which is about like gigabytes to terabytes, and also further leverage the solid state disk or disk storage, which increase this amount of this storage or memory system hierarchy by another level, we can potentially leverage one single GPU plus SSD to enable such big AI models to be deployed, so that we do not necessarily need to purchase this like 8X B200 GPU, multi-node GPU to enable that, well as we can deploy that in one single GPU plus SSD. So that's the long story short, or like the motivation we want to do this. But it's not easy, because in order to do that, we need to coordinate all those communication, like how we move the data, how we should do those cache coherence design in terms of when we cache the data, where we cache the data. Should we cache the data in the CPU DRAM? Should we cache the data in the GPU DRAM? Sorry, GPU GDDR or HBM memory? So these are all the questions we need to solve in order to enable such kind of a system level acceleration. And we did some research. We did explore this part, and also that's exactly we propose Agile, which is the asynchronous I/O between those GPU and SSD. And before I discuss how Agile is working, I also want to share a demo which we deploy on the website to explain this fireworks on how we coordinate the data movement in this computing system, and nowadays how Agile is working on those data movement between the computing system. So before Agile, if the GPU needs certain data from storage, in this case it's NVMe, non-volatile memory, the GPU needs to first talk to CPU, and the CPU then initiate this storage or IO movement, and then send that to those non-volatile memory. And non-volatile memory data will be first moved to the CPU DRAM for the cache, and then move that data back to the GPU. So you see there are many hops here, right? So if we can skip the CPU control in this way, can we reduce the system latency and also increase this energy efficiency? That's exactly something we want to pursue, and that's exactly what we enable in Agile. So this case 3 is exactly Agile enabled. So in Agile project, we allow this GPU to directly talk to the non-volatile memory and then fetch the data from those storage system to the GPU, while skipping those data paths and also control paths on the CPU memory and also CPU compute. So this is exactly the idea. And this gives us those both in terms of the latency reduction and also energy efficiency gain. And then the question is like, how can I use Agile in my own application, right? So we provide Agile APIs. So this way it's give you like an API example about how you enable API. So if you specify the data that's this is a data chunk of A and another data chunk of B, and then you call Agile API to say, okay, I want to do read asynchronous, which means that I would like to call Agile API to asynchronize read the data from those storage, and then I'll just ask this data control or the IO initiation starts, and then I'll just compute in another module, which is the previous data I already fetched from this storage. While at the same time, I can do I can fetch the new batch of data. So this compute module on those previous chunk of data and these fetching data on this current chunk of data can be overlapped. So this exactly is the key idea of asynchronous I/O, which allow us to overlap these I/O transfer data and the compute module so that we can increase this amount of data in certain time. That is a throughput in reading the data and also throughput in terms of computation. So we port this Agile design on several GPU platforms to verify whether it can be generalized, and the answer is yes. We now provide Agile API in terms of this host code and also this device code change, and we can now users, if they want to use Agile as a service, they can change the code in certain ways. So here I show like 3 methods in enabling Agile services. And then this right-hand side is the code that they need to update in the host side to enable Agile services. So the key idea is that this is one demo user cases we show on top of Spectrum node, is that with this computing system where you do have the GPU and also this storage in the same PCI, in the same server node, then you can now call those Agile API to enable those Agile asynchronous I/O within the single CPU, within the single server node to allow those system level acceleration. And another question or extended question is that in the future, what users need to do if they do not want to change their device code or host code. So this is exactly what we are now working on, is that if we provide another layer of abstraction, and then users can further call Agile without writing or rewrite their code. So they just call, or they can just specify a flag as Agile use from 0 to 1, and then this Agile services under the hood will take care of all those I/O sent from the GPU to the storage, and then insert certain API, and then can. This is an easy way for any users to easily adopt Agile services in the future. So long story short is that we're now in phase that the users needs to change or update their code and then recompile the source code. But in the future, we do want to abstract the Agile in a service like deployment environment, and then user can use Agile without even changing their code. So this is the one example about how system software on top of Spectrum hardware compute node, and then it can allow or enable system level innovation and deployment acceleration. So this is like the user case 1, right? And for now, I think this is give you some of those interested in using this. But by the way, I'll skip this 3 slides. But another question is that if you want to use the FPGA compute nodes in those Spectrum compute node, how we can do that? So the FPGA is in a very similar way to be used as is GPU. So in the GPU, you have those code being compiled, and also you run the binary, right? But in the FPGA, you do the similar thing. This is one example about the graphic user interface in Syracuse node. So in the future, for Spectrum users, they can first log into Fabric and then connect it to Spectrum node, access node first, and then use the jump node to use the Spectrum compute node. And this will be the interface if they use GUI as this access. And they can also use a remote server access, like the terminal access. So this is the right-hand side is the terminal access interface. So this is well, you can first connect it to those jump server, and then you can download the bitstream that you have pre-compiled on top of the FPGA architecture, and then you can connect it to the compute FPGA card, and then reboot this compute FPGA card, and then execute the bitstream. That is your application on top of that, and receive the data or send the data to FPGA. So this is the overall flow. And we are actively working on this so that users can easily use either the GUI interface or using this remote access terminal interface to first port their design, deploy their design, and also move their data into the Spectrum node. So this here is all those user interfaces system level deployment that we have been working on and also completed. So we are actually working with both Fabric team and also Syracuse IT team to enable this user interface we plan to deploy. And also another important thing is that we also want the users to provision the compute in terms of how many number of GPUs, how many number of FPGAs they want to use for their experiment. So for now, we are discussing with the Syracuse team whether we can either design a queue system or either design a subscription system so that the users can say like they want to schedule 4 FPGA plus 4 GPU to be used this afternoon. So this has been in a work in progress. And in parallel, we're also working on providing all those like a demo example, the FPGA onboard example, and also this reusable experiment template, including both the GPU deployment environment, FPGA deploy environment, and also GPU SSD or FPGA SSD deploy environment, so that the users in the future can just launch this example experiment to start, and also based on those example code, they can update and also change the code and deploy their own application. And in addition to Agile project, we do collaborate with many domain experts to work on some other autonomous system accelerator design while using Spectrum. You may wondering, well, this is a picture on the edge, like a physical intelligence on the edge, right? How can Spectrum be helpful in a compute node in the data center? How can a compute node in the data center help those edge compute scenario? Well, this is because before you deploy any customized computing system on the edge, you first need to fully verify, test, and also make sure that all those corner cases has been fully verified, right? And this is exactly we can leverage Spectrum compute node to do those design tests in the first place. So this is particular project is Mavericks project that I collaborated with Dr. Weisong Shi from University of Delaware, who is the lead PI for those CAR and NSF IUCIC Center, and also Dr. Zheng Dong from Wayne State University. So we work together on this, enabling software and hardware co-design for autonomous system. Dr. Weisong Shi and Dr. Dong, they provide all those applications, and we in Brown team provide all those computing systems and also customized computer chips for next generation autonomous system. And we published several papers on designing how to do those customized computing chips in the single chip level and also in the node level, so that we can guarantee all those applications that run on autonomous system, including the vision classification, including the LiDAR or LiDAR, all those multimodality sensor processing plus computation together can run efficiently on those customized chip environment, and also while meeting those safety critical requirement. So now we are at the phase that this chip has been designed, and then we are very excited and looking forward to bring those chips into those cars in Dr. Weisong Shi's lab. So that's the next step we're going to do. That is to port the design we have designed and to test it on Spectrum node, and then to the edge, the real world application in the edge. So here's another example, also working with a domain expert. This is my collaboration with Dr. Albert Tao at the University of Pittsburgh. So they have this they have this 3D printing machine for metal. So they have a gigantic printing additive manufacturing facility in University of Pittsburgh, and then they want to use those real-time intelligence system, including those video analysis and also AI inference, so that they understand that after one layer of metal printing, whether they are defects, and if they are defects, they can remove this layer. So this is good because previously they can only like detect all the things after this artifact has been printed. This usually takes about hours, and then if you find a defect, you have to discard the whole thing. So that's not good. So with this in time, on the fly defect detection with this video processing accelerator deployed on the edge, we can reduce this like wait time, and also we can increase this quality for those printed materials. So this is also an ongoing collaboration effort, and we are also working to port all those design from the spectrum computing environment to those edge compute in the Dr. Abel Tao's lab in University of Pittsburgh. So another example this way, this is a very cool picture, and also another example of about working with domain expert. Here's my collaboration effort with Dr. Kevin Chen at Pitt ECE department. So Dr. Kevin Chen has those optical sensing processing unit, right? And I have the compute unit. And then together, for example, if you deploy those sensor in the fiber optic sensors in a facility, like in this way, this is a picture to show that Dr. Chen and his student deploy those fiber sensors in this hallway in ECE department at Pitt. And then using those sensors, you can actually detect the pedestrian height and weight without capturing their faces. So compared to those image processing or compared to those camera-based detection system, this is the perfect way to do privacy preserving computing and also privacy preserving pedestrian detection. And the right-hand side shows the accelerator that we have deployed on FPGA. By the way, this is published in 2024 ACM Chats Journal, FiberFlex. You are more than welcome to check this paper. And also, I also would like to mention that we are actively working with the Brown Digital Health. This is the collaboration effort within Brown Engineer that bring together all different discipline, professors and also researchers and also medical practitioners, that how we can enable edge AI for more broad medical applications. So that is this is pretty a new project. Now we are working at Brown Engineer, but we do want to bring this professors in optical sensing, in this mechanical sensor, and also in this vision classification, vision computer vision, and also the medical doctor, and also Aging in Place, which is a nonprofit organization in Rhode Island, so that we can design, for example, those smart in-home techniques to detect fall detection, so that we can help those aging in place or help also personalized medical care deployed in a home environment. So these are all those exciting projects. Now we are exploring to use a Spectrum compute node to first design and test and verify all those computing systems before move them to the edge computing scenarios. So with that saying, I think it's 43 minutes already. And then with that saying, I'm happy to take on questions from the audience. But I also want to highlight that if you are interested in joining Spectrum Computer node as a early users, please reach out to student lead Shixin Ji, who is my senior year PhD student, or also CC me, copy me in the email to discuss your need and also get started. So we are very, very looking forward to welcome our first batch of users this fall semester. And also we are really excited to work with Fabric together to bring those Spectrum compute infrastructure to broader user in our community. And thank you all, and happy to take any questions.
Thank you, Peipei. So now
thank you, Dr. Wang.
We'll move on to the Q&A session. We'll now stop the screen sharing and begin addressing the questions, starting with those submitted during the presentation. All right, I have the first question here. FPGAs are in general very expensive hardware to buy for academic researchers compared to consumer-level GPU cards to add to their desktop. Are there similar consumer-level FPGAs in the market for one to buy and experiment on their desktop?
Well, this is a very, very great question. So honestly speaking, there are some like embedded FPGA. By the way, I'm not advocating for either like AMD or or Altera in this case, but I do encourage you also can reach out to AMD University program and also this Intel. No, the Altera University program to have your hardware being donated. So I personally got donated if with certain project justification, but I also buy FPGA cards for my teaching courses at Pittsburgh and also at Brown University. So at that time, we use the Zinc board, the Z board. You can search if you're interested in those Zinc FPGA board. It's pretty cheap. I think it's about like $50 to $100, depending on this what kind of FPGA chip you want to use. But if you want to try some of those FPGA cards just to get started, you can feel free to reach out to us, right? Because the Spectrum node now has FPGA board in the data center, so we should be able to allow you to try the Hello World example on FPGA cards sitting in Spectrum node.
That sounds good. The next question: how will users specify their hardware mix and interconnects they need in the experiment?
So this is a pretty great question. So actually, we are actively working on this this flow. So in my phase 0 like deployment environment, actually the student has these root access, but we cannot allow the users any like users to have root access, right? To specify the mix. But we do have an idea is that we this is a very like early phases, but we do want to specify certain like markdown format to allow users to specify how many number of GPU they want to use in which node. So for now, we have 2 compute nodes. In the future, we'll have 3 compute nodes. Together, there will be different GPUs on number of GPUs within those 3 different nodes. So the user need to specify number of GPUs, number of FPGA in which node they need, and then they have to wait until all the resources are available. So they are working. We are actually working on this flow right now.
And the next question, I think you're already talking into it. Will Spectrum have its own user interface for reserving and configuring their resources, or will users be using Fabric-style tools?
So, so we will use a Spectrum like a node. So Fabric will provide an entry phase or entry point for users to access Spectrum node. So this is how users use Spectrum. So we will first use Fabric and then connect to Spectrum jump node and then use the Spectrum node. But then within Spectrum, then that's a Spectrum configuration GUI and also a user interface.
That's great. Next question: how will researchers bring their own data into Spectrum for replay or evaluation?
Yeah, so this is a very important question. So we do allow users to SCP like move their data from their own like local servers to those remote servers on Spectrum, and also you need to specify this this node whether only you can see the data or anyone on Spectrum node can see the data. So we will allow users to configure that as well.
All right. So the next question: what starter examples or packaged workflows will be available to help new users begin experimenting on Spectrum?
So we now have those ready to be deployed example, including the source code and also the compilation flow for FPGA and the GPU as well. So now we are working on porting more example codes so that you can kind of think that when the first batch of users start to use Spectrum, they will see a few examples. And then when more people are using, they can contribute into this example so that we have more such kind of like a starting point. Yeah. But now we do have FPGA and the GPU as well.
Okay, and now I think we have our last question. How will Spectrum connect with Fabric as a facility port connected system or through deeper software integration?
So this is a great question. For now, we are adopting this facility port connected system, but we do have this plan, and actually that's some questions that we are working closely with Fabricating about how we can configure this network also, right? Because we can now configure the GPU, FPGA, accelerator. However, if we can configure a network system in the whole like large scale computing setup, then that would be great. So this is something that we can certainly explore in the future.
All right. Well, thank you. I think that will wrap up our Q&A session. So thanks again to our presenters, Dr. Peipei Zhou. So now moving on, in addition to our presenter, we will also like to acknowledge the behind the scenes team who worked diligently to bring this webinar to production. So the Fabric team member, Chelsea Davis, is our project manager, and myself have been working on this. Thank you for the audience for your participation today in the webinar. In addition to the recording of it, we will also be emailing a list of resources we'll also be emailing a list of resources for the experiments that you can consider. And then going forward, there will be our next webinar coming up. So that will be the Mastering Fabric Tips and Tricks webinar on September 15 at 3 p.m. Eastern Time. This next webinar will be focused on existing users, AI researchers, and testbed administrators who will want to go deeper with their experiments. We would appreciate it if you could forward this information to anyone, any relevant users in your communities. As a final reminder, please submit your Fabric matrix if you're existing Fabric users, and make sure your project description in the portal is up to date, because we do use those information for outreach and promoting your work. And thank you again. Have a wonderful day.
Thank you, Dr. Wang and Chelsea, for moderating this session. And thank you all. And feel free to reach out. I also probably available all the time on the email. So this is the easiest way to find me. Yeah, thank you.